Hello, my name is Kindson the Genius, and today we are going to be discussing maximum likelihood estimation. Now, maximum likelihood estimation is a very important concept in machine learning, data science, and statistics. So we are going to be deriving the formula. So if you have a pen and a note, please take a note of jot down this formula so that when we derive it, it becomes a little clearer. In this lesson, we are going to cover a review of the least squares estimation. We are going to mention the goal of maximum likelihood estimation. What is maximum likelihood estimation? Background of maximum likelihood estimation. And very important, we have this from just a second. Okay, this formula, we are going to derive it. The formula I showed you previously. Then we are going to briefly mention the log likelihood function, and then we are going to now summarize what we've learned so far. It's going to be brief, so let's start. Why I decide to mention least squares estimation is because least square estimation, just like maximum likelihood estimation, is an estimation technique used in analysis. In case of least square estimation, you fit a regression line through your data points, and then you calculate the deviation of each data point from your regression line. You take the square of all these differences, and then you total them up or you sum them up and try to get the minimum of this. The sum of this is called the error function. Now, in case of maximum likelihood estimation, we are going to be using probability density function. In least squares, we mentioned the error function, and here we are going to be using probability density function and also the likelihood function. Now we have that in case of MLE, we have a data set of, let's say, n observations, and we are trying to fit it through a probability density. We are trying to fit a probability density function through the data set. We are going to assume that this data set is normally distributed. The goal of maximum likelihood estimation is to fit a distribution to a data set, and it assumes that the data set is normally distributed. It tries to find the likelihood function and maximizes the likelihood function. So what we are saying is this. We are saying that we have a series of observation x1, x2 up to xn. Now we are trying to fit a distribution through this series of values. What it means is that we actually may decide to choose a parameter for this distribution and then try to check if these observations are correct. So let's explain a little more. Maximum likelihood estimation estimates the parameter of a model given the observation, and then it tries to find the parameter value that maximizes the likelihood of making the observation given the parameter. So it's like a two-way analysis. First of all, we fit a model to the observation. We assume that it's based on a particular model, and in this case it will be a probability distribution, and then we choose a parameter value, and then we try to maximize the likelihood that this parameter value is correct, and effectively that these observations are also correct. So let's assume you have 10 beds that you've measured. This is your sample of heights of these beds, height of h1 to 10. Now you want to find the parameter of the distribution or the population. Now 10 beds they are very small. We have thousands of beds there, but you want to use this 10 to find out what the population or the parameters of the population will look like. Of course, there are a number of parameters that we can try to determine. Now, maximum likelihood selects the value of parameters that maximize the likelihood function. Alright, let's see. Take for example something like no, let's okay, so alright, so explaining a little further, we are saying that we have just a second. Okay, so we have x1, x2, x3, xn. Okay, and now we want to find the likelihood that a given parameter, let's call this parameter theta. Okay, we want to find the likelihood of this parameter. Okay, it will be the distribution, sorry, it will be a function of the samples okay, of the samples given the parameter. So that is what it will be. So where theta is the parameter of the distribution, which actually is unknown. Okay, so and this actually is the likelihood function of this parameter. So now we are saying that maybe I'll just get to the screen where we are going to just try to derive this formula. Alright, so let's try to work on deriving this formula at this point. Let me use a black ink. Okay, so so we have f of x1, x2, x3 all the way to xn. Okay, and now let's the likelihood that this parameter is correct be the function of the observations given this parameter. Okay, alright, so we can now make this function a product or a sum of the univariate, so it will also give us the same thing. So what it will mean, we can split this to be f of x1 given theta plus f of x2 given theta plus f of xn given theta. Okay, so now we can now take the sum, and the sum will be the sum of all of these will just be, let's use the symbol for I equal to 1 to n. and you have f of xi given theta. So the question now is, having found the likelihood function, how do we get maximum likelihood estimate? Remember, we mentioned that the data is normally distributed, something like this. Okay, so we have this is theta, and we have this is L theta. So what it means is that we can now maximize this function. If we maximize this function, it means that we are going to have the maximum estimate for this function. Alright, so having said this, we can now try to figure out how to do this. It actually will be very complex way of doing things. So what we are going to do is to find an easier way to handle this. And one way to do that is to use log, a log function. And that is where we have something like log likelihood, log likelihood. So what it means, instead of maximizing the likelihood function, we replace the likelihood, we replace it with the log of the function. So we can now say log of the likelihood will be I equals 1 to n. We take the sum of the likelihood function xi given theta. Okay. So if we've gotten to this point, then at least we've derived the logarithm of the likelihood. So what we are going to do next is to maximize using calculus methods. So that is the way to maximize. Alright, so basically that is how it works. But I've also made a note of the algorithms in case you want to just read to see what the algorithm is doing. So there are 3 steps of the algorithm. We have take the derivative of the function, set the derivative to be 0, and solve for lambda. This lambda is also the parameter which we called theta in the previous slide. So we find a solution that makes this parameter to be maximum, and that is where the derivative is equal to 0. So we are going to stop here, and if this is informative for you, subscribe. If not, leave a comment, let me know. Maybe I'll have to do a little more explanation on this. I'd like to thank you for viewing.